Well, it's time to introduce the last of the 6 inverse trigonometric functions, and that is the arccotangent. So, of course, we introduce this very similar way that we introduce the others. We look at the cotangent of x, and then we graph the line y equals x. If we do its inverse, we get x equals cotangent of y, which we see is definitely not a function. I think you can see the reflection going on here, but it doesn't turn out to be a function because the cotangent is not 1-to-1. So we want to restrict this down, and it's pretty natural to pick, well, we're going to pick between, we actually could pick either between negative pi over 2 and pi over 2, or between 0 and pi over 2, just like we did with tangent. Okay, where's tangent? Right here. Notice we could go between negative pi over 2 and pi over 2, or between 0 and pi over 2, and we would still get all the y's used once. But what do we do for tangent? We like to pick it so that it's one connected piece. So we chose tangent to restrict from minus pi over 2 to pi over 2. So in a similar manner, we would like this to be one connected piece. So the reasonable thing to do is to connect it from 0 to pi, and then you get one connected piece here. And so you get, not only is it 1-to-1, it is continuous. So when we can get a continuous function for our restricted version of the trig function, that's what we're going to do. And we were able to do that in tangent and cotangent. And of course we were also able to do that in sine and cosine. Secant and cosecant, that wasn't a possibility for us. So that's the part that we're going to take, just that part, and reflect that over the axis, and we get y equals arccotangent of x. Okay, except we're not supposed to get all of this, so let me fix this right. What's it supposed to do? We're actually only supposed to keep the part going from 0 to pi. And there is our function that we're after. And that's the arccotangent. Okay? Notice it was part of that function, that relation x equals cotangent of y, but is just this part here. Now, let's try to remember how we did this calculation before. Let's do a similar thing. There's not an arccotangent function on your calculator, so we want to graph y equals arccotangent or inverse cotangent of x. Well, this means this is part of cotangent of y equals x. But which part? X is the output of cotangent, or the input for inverse cotangent, and that's from minus infinity to negative 1, or union 1 to infinity. We want to keep the entire range of the cotangent as our input for inverse cotangent, which we've done. But what did we selected an output, and we selected it from 0 to pi here. Okay, so we could try to do this like we did before. 1 over tangent of y equals x. So tangent of y equals 1 over x. Everything's going just fine, but we run into a problem when we try to do y equals inverse tangent of 1 over x. Because the inverse tangent of 1 over x, this y is between minus pi over 2 and pi over 2. See, these don't match. So, inverse cotangent of x is not the same thing as inverse tangent of 1 over x. And I can show you that. I think I can show you that here. Here's the graph of inverse cotangent, and it puts a it's that part in black there. And notice how that agrees with for the positive part, for positive x's, that agrees to give me a value between 0 and pi, but it doesn't give me the right thing here. So what do I need to do? I need to shift this part up. How far do I need to shift it up? Well, it has an asymptote of 0, and we need to shift that up to pi. So we need to shift this part up by pi. So you can see right here is the actual definition, or one way you can do the inverse arccotangent in your calculator, but it's a little bit problematic because it's actually a piecewise defined function. It is the arctangent of 1 over x for positive x's. It's pi over 2 when x is 0. Of course, x is 0. Arctangent of 1 over x is undefined because the 1 over x is undefined. And it's pi plus the arctangent of 1 over x for x's that are negative. And we'll see that that one does give us the right graph. It doesn't give us that graph. It gives us the correct graph that we're after. Okay, so let's do that on the calculator. Now, we've got to be a little bit careful because we've got a piecewise defined function. So y equals the inverse cotangent of x, or arccotangent, and that y will equal the inverse tangent of 1 over x if x is greater than 0. It'll equal pi over 2 when x equals 0, and it'll equal pi plus the inverse tangent of 1 over x for x is less than 0. Now here's how we'll put this in the calculator. You put in inverse tangent of 1 over x, and then you put x greater than 0 in parentheses, plus, you put in pi over 2, let's put in parentheses, and then put in x equals 0, and then plus, parentheses, pi plus inverse tangent of 1 over x, close parentheses, and put in x less than 0. Now let me explain this a little bit because piecewise defined functions in your calculator are a little bit tricky. And so what did this do? Well, these statements are statements that are going to be true or false on the calculator. So if they're true, they return a value of 1. If they're false, they return a value 0. So if x is greater than 0, this one's true, so it returns 1. These two are false, so they return 0. The zeros are going to wipe out everything here. The 1 times this would just leave the inverse tangent, which you want. Well, what if x is equal to 0? Well, this one will be 0, that one will be 0, this one will be 1, and then it would only leave pi over 2. Finally, if x is greater than 0, this one would be true, so it would return 1. These two would be false, so it would wipe those out. This would be 1, and so it would keep this. And we'll see that this will graph it correctly. Okay, it's complicated to put in, but there it is. So it's inverse tangent of 1 over x times, and then x. Now the greater than, less than you get under the test menu. Greater than 0, so that's number 3. Plus, parentheses, pi over 2. And parentheses, x equals 0, plus, parentheses, pi plus the inverse tangent of 1 over x, and x less than 0. So let's graph that, and I believe we'll see that we get the graph looking like we want it to look. One connected piece. So that does work out correctly. Okay, so that is the inverse cotangent. Okay, so let's look at some of its properties. The domain is all reals. You can see it goes over all reals here. Its range is 0 to infinity. No, wrong. Its range is from 0 to pi, but it does not include 0 or pi. It right halfway in the middle, right here on the axis, right there, is an inflection point. Okay, and that point is also, of course, the y-intercept, and that point is the point 0, comma pi over 2. It doesn't have an x-intercept. It has horizontal asymptotes at y equals 0, the x-axis, and also at y equals pi on the left, and y equals x on the right, y equals 0 on the right. It is a continuous, meaning it's one connected piece, decreasing, going down from left to right, one-to-one function. It's concave down in the second quadrant here when x is negative, and it's concave up in the first quadrant when x is positive. The output of the y you can think of as in the unit circle picture here as a rotational angle, which is somewhere between 0 and pi. Of course, it can't actually be 0 or pi, but it does include everything in between. Let me indicate it can't be 0 or pi by making these white, but it's definitely still in between 0 and pi somewhere. Okay. It's true to say it's in the closed interval 0 to pi, but I could actually be more explicit and say it actually can't be 0 or pi, because if you have an angle of 0 pi, cotangent is undefined. And so now we can see there are the properties of the arccotangent. And again, here's what we just worked out for the thinking of it as a piecewise defined function in terms of arctangent. Okay, and that concludes our basic introduction to these. By the way, if I go back here to transformations 2, just to show you, this does have, let's see, where's our, there's the arc sine, but this also has a times arc sine of b times x minus h plus k, and so we can manipulate these parameters and transform it like we can any other function. There's arc cosine and there's arc tangent, and so we can transform, we can play a little transformation game like we did with our other functions on that on this particular sheet here as well. Okay, so I think we've got a fairly decent introduction to all the inverse trigonometric functions, and now that we know what they are and what the domains and ranges are, we can put them to work. Notice that basically, let me kind of look at this picture right here. Let me just kind of sketch that over here kind of sloppily. But if you look at it, we're always restricted, if we think of the unit circle, we're always restricted either to this part here going from 0 to pi, so that we have an angle somewhere between 0 and pi radians, or we restrict it this way so that it's on this part somewhere between minus pi over 2 and pi over 2. And so we restrict our domains of our trig functions to one of those two intervals in such a way that it's a one-to-one function, and then when we're given a choice, tangent and cotangent, we pick it to be a continuous function. So what did that turn out to be? So this one, sine repeats itself, so sine can't be here, but cosine works here. So inverse cosine would give us an output between 0 and pi. Inverse sine gives us an output so if we do y equals inverse cosine, y equals inverse sine of x, then the y value is going to be something here. Let me call it theta. So for our theta value, alright, and maybe we'll use another letter altogether, let's say z, so we're not confused with the x's and y's on this picture. Okay. So that's sine and cosine. What about tangent? Tangent was, when we restrict tangent, we restrict it to be between, in this region right here, so inverse tangent of something gives us an angle that's between here. Inverse cotangent was different. It was between 0 and pi. And what about inverse secant? Inverse secant was this one over here, same as cosine. The theta would be here, and the inverse cosecant same as sine. So that gives you a basic picture. If you can just kind of remember this picture here, that can help you remember which one. And of course, some of these, there's an undefined point either at one end point or the other, or right in the middle. But the basic idea is you're getting something from 0 to pi, or something from negative pi over 2 to pi over 2. And you got those two things there that you can kind of keep track of that. So if you have something like, if I say y equals sine of y equals sine of x, and then I put in a specific value for y. So if I say like sine of x is 1/2, let's say, okay, then how many places can that actually happen? Well, there are actually infinitely many rotational angles that this can occur. Okay, and for example, I take a circle of radius 2. We could take here or here for our terminal side. This is 2. This is 1. This is 2. This is 1. This is square root of 3. Square root of 3. And so any angle that's going to end here or here will do it. But specifically, this angle that's in this part right here, right, between negative pi over 2 and pi over 2, is going to be, this is theta, which is arc sine, or inverse sine, of 1/2. It's a specific one. Well, we know what it is, right? So it's specifically pi over what? 3. Okay, 60 degrees. But of course, that's not the only solution. So sine of theta is 1/2. So one possibility is this inverse sine. It gives you a very specific one. Well, there are infinitely many rotational angles that will give you that same value. Okay, and what are all those? Well, they're pi over 3 plus 2n pi. But there's also one right here that gives you a different terminal side, and it still has the same sign. It also has a sine of 1/2. That one is, well, it's 2 pi over 3 actually, is one way to say it. So you can also get 2 pi over 3, and then any multiple of 2 pi added to that. So if we wanted to solve the equation, sine of theta equals 1/2, then we actually get, that happens if and only if theta is an element of this set. It's pi over 3 plus 2n pi, or 2 pi over 3 plus 2n pi, such that n is any integer. Okay, but so that gives us infinitely many. There are infinitely many angles here that have this same terminal side in the first quadrant, and there are also infinitely many angles that have this side in the second quadrant. So there are two groups here, two sets, two different two different terminal sides when you put it in standard position, but infinitely many rotational angles within that. So there are infinitely many solutions to this. Okay, but only one of them, if I said theta equals inverse sine of 1/2, that's very specifically just pi over 3 only. Only that one particular one. Okay, so I think that gives us a basic introduction to the inverse trigonometric functions.